Today, I'm going to talk about the just announced Nobel Prize in Physics for 2022. Go to Elaine Aspect, John Clauser, and Anton Zeiliger. And the main issue here is they showed how quantum entanglement has become a powerful tool for humans. So using groundbreaking experiments, Alan Aspect, John Clauser, and Anton Zeiliger have demonstrated the potential to investigate and control particles that are in entangled states. What happens to one particle in an entangled pair determines what happens to the other, even if they're really too far apart to affect each other. The laureate's development of experimental tools has laid foundation of a new area in quantum technology. This is quantum computing, quantum communication, quantum encryption, and so forth. Okay, so first we got to go back, because this is very complicated and sophisticated. We got to go back and talk about the various aspects. The first thing is quantum mechanics. So quantum mechanics has become a well-established theory that allows us to calculate things very correctly and to very great precision. It's been tested in many experiments and known to provide the correct answers. However, it has properties that are far away from our everyday practical experience, and some of these seemed actually contradictory to us. One of those is that it's a probabilistic theory. That is, it's a theory that doesn't tell you stuff exactly. It just tells you that things will happen with a certain probability, and that what actually happens is stochastic, random, in terms of falling in those probabilities. Another thing that it tells us is that fundamental particles of a given kind are all exactly identical and can interfere with each other constructively or destructively. And one more critical aspect of everything is in a discrete quantum state. That is, there are only certain allowed states, not a continuum of states, but a certainly allowed states. And everything is in a quantum state. And sometimes they're in a superposition of many quantum states. That is, they're in two or more states at the same time. A very extreme example of that is the famous Schrödinger's cat, which is hidden in a box from the observer and exists in the superposition of both being dead and alive. And there's much discussion about that in the past. These features lead naturally to quantum entanglement. And the simplest example that is two identical particles that are quantum entangled, measuring one way over here tells us about another, which is way over here, even though they're very far apart. That's a key and important issue. This is disturbing to a lot of people. Quantum mechanics was very disturbing to Einstein because he didn't think that things should be probabilistic, but it should be well determined. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen pointed out that in situations involving specially prepared particles, that is, the particles here that are quantum entangled, that are far apart, this unorthodox principle conflicts with locality, the idea that information can't be traded faster than the speed of light from one place to another. Unfortunately, the role of locality in the discussion is often misunderstood or even missed entirely. One often hears that the EBR paper is essentially an expression of Einstein's philosophical discontent with quantum theory. This is quite wrong. What the paper actually contains is an argument showing if non-local influences are forbidden, and if certain quantum theoretical predictions are correct, then the measurement whose outcomes are correlated must be revealing pre-existing values. It is on this basis, in particular on the assumption of locality, that EPR claimed to establish the incompleteness of orthodox quantum theory, which denies the existence of any pre-existing values. It's basically saying there should be some hidden variables if things are going to be local. Now, John Bell eventually created a theorem which asserts that if certain predictions of quantum mechanics are correct, then our world is non-local. Non-local here means there exist interactions between the events that are too far apart in space and too close together in time for them to be connected by signals moving even at the speed of light. This theorem was proven in 1964 by John Stuart Bell and has in recent decades been the subject of extensive analysis, discussion, and development by both physicists and philosophers of science. Bell's theorem now is a term encompassing a number of closely related results in physics, all of which determine that quantum mechanics is incompatible with a local hidden variable theory. That is, that there's some hidden variables, then the whole thing is, then when you understand that, is a local theory, and there's no contradiction with relativity. Local in this case refers to the principle of locality, the idea that a particle can only be influenced by its immediate surroundings, and that the interactions mediated by physical fields can only occur at speeds no greater than the speed of light. Hidden variables are hypothetical properties possessed by quantum particles, properties that are undetectable but are still affect the outcome of the experiments. In the word of physicist John Stuart Bell, for whom this family result is named, if a hidden variable theory is local, it will not agree with quantum mechanics, and if it agrees with quantum mechanics, then it will not be local. This term is broadly applied to a number of different derivations, the first of which was introduced by John Stuart Bell in the 1964 paper. Bell's paper was a response to a 1935 thought experiment that Albert Einstein, Boris Podolsky, and Nathan Rosen used to argue about quantum mechanics being an incomplete theory. Already by 1935, it was recognized that quantum mechanics was an accurate theory, but it was recognized that traditional quantum mechanics are probabilistic. Einstein, Podolsky, and Rosen presented a scenario that involves preparing pairs of particles such that the quantum state of the pair is entangled and the separation of the particles to an arbitrarily large distance. The experiment has a choice of possible measurements that can be formed in one of the particles. When they choose the measurement and obtain the result, the quantum state of the other particle apparently collapses instantaneously to the new state, depending on that result, no matter how far away that particle is. This seems pretty contradictory, and this suggests that either the measurement of the first particle has somehow interacted with the second particle at faster than the speed of light, or that the entangled particles had some unmeasured property which predetermined their final quantum states before they were separated. Thus, assuming locality, quantum mechanics must be incomplete because it can't give us a complete description of the particle's true physical characteristics. In other words, quantum particles, like electrons and photons, must carry some property or attribute not included in the quantum theory, and uncertainties in quantum theory predictions will be due to the ignorance or unknowability of these properties, later termed hidden variables. This is when our heroes show up. John Clauser became interested in the fundamental question of quantum mechanics as a student in the 1960s. He could not shake the John Bell's idea once he read about it, and eventually he and 3 other researchers were able to present a proposal for a realistic type of experiment that could be used to test the Bell inequality. Stuart Friedman, a professor of physics at the University of California at Berkeley, who I knew very well and worked with, but who unfortunately died at the age of 68 as a graduate student, and John Clauser as his advisor, published the first test in 1972. John Clauser had immediately started working on conducting this experiment. He built the apparatus that emitted 2 entangled photons at the time. And along with his doctoral student, Stuart Friedman, he was able to show a result that would clear a violation of Bell's inequality and agreed with the predictions of quantum mechanics. There are no hidden variables according to them. In the years that followed, John Clauser and other physicists continued discussing the experiment and its limitations. One of these was that the experiment was generally inefficient when it came to both producing and capturing the particles. The measurements are also preset with the filters at fixed angles. As a consequence, there were loopholes where an observer could question the results. What if the experimental setup is in some way selected the particles that happened to have strong correlation and did not detect others? If so, the particles could be carrying hidden information. Eliminating this particular loophole was difficult because the intertwined quantum states are so fragile and difficult to manage. It is necessary to deal with individual photons. French doctoral student Alain Aspect was not intimidated, as the young people are bold and try stuff that more serious, older people will think is too difficult. Alain built a new version of the setup that he refined over several interactions. In his experiment, he could register the photons that passed through the filter and those that did not. This meant more photons were detected and the measurements were better. In the final variant of his test, he was also able to steer the photons to 2 different filters that were set at different angles. The finesse was a mechanism that switched the direction of the entangled photons after they had been created and emitted from their sources. So it's not that hidden variables that started together. They were fixed when they were far apart already by choosing how things are going. The filters were just 6 meters away, so the switch had to occur in a few billionths of a second. Information about which filter the photon would arrive and influence how it was emitted from the source. It would not arrive at that filter, nor could information about the filters do it. So even though it was only 6 meters in size, he was able to make things happen quickly enough that he can close that loophole. So he imposed that Alain Aspect close that important loophole, and provided a very clear result in quantum mechanics is correct, and there are no hidden variables. He gets the credit for making the first truly convincing sort of airtight experiment, and that was in 1982. And since then, his results have been more convincingly reconfirmed many times. Given Bell's theorem, these experiments establish our world is non-local. This conclusion is very surprising since no locality is taken to be prohibited by relativity. So a paradox here, I think it can be solved in a couple of other ways, but we don't have to worry about it because right now we're celebrating the fact that he proved that this is the case and that we can start using quantum entanglement to do many other things. We now enter the era of quantum information. These and similar experiments have made the foundation for the current intense research in quantum information science. And being able to manipulate and manage quantum states and all their layers of properties give us access to tools with unexpected potential. This is the basis for quantum computing, the transfer and storage of quantum information, algorithms for quantum encryption, and systems with more than two particles, all of which are entangled, are now in use, which Anton Zeiliger, and the third person, and his colleagues were the first to explore. And so they get the credit for being the pioneers in the field. In China, we know that people take this seriously enough because it's an entire satellite system. The Chinese mucus quantum satellite was put into orbit especially to test if you could do quantum encrypted information transfer. And from Xinjiang, the signal was sent to the satellite. That was also sent to a ground station in China, but also to Graz, to Anton Zeiliger's research group. So they are able to transmit quantum encrypted information up to a satellite and back down to the ground and be confident that that signal got there and it was pure. It wasn't seen by someone else, but only passed between the two of them. This Nobel Prize makes a mark that they were pioneers in setting us on this path now to quantum information systems. So thank you very much.